The problem states, draw shear and moment diagrams for the simply supported beam. So at first, we want to do an overall equilibrium for this beam because we see that it is supported in points A and B. However, we do not know what those forces are. So let's start off. Drawing this free body diagram, we have the beam. We have a force at A, and we're going to call this simply force A. And we have the force at B, and we also have the load as 9 kilonewtons. Now, these forces are certain distances away from each other. When we drop a vertical axis from each of these forces, we see that between A and the 9 kilonewton force, it's 4 meters. Between the 9 kilonewton force and B, it is 2 meters. Now we have enough information to solve this equilibrium problem because we have the two unknown forces, but we know that since it is in equilibrium, the total summation of forces in the y direction is equal to 0, and we also know that this total summation of moments is also equal to 0. And let's pick a point to calculate our summation of moments about. Let's call it point A. Let's pick point A, and that is equal to 0. Now, let's solve these equations. What is our total summation of forces in the vertical direction? So we have force A plus force B minus 9 kilonewtons. For summation of moments about point A, we have an overall clockwise contribution for this this vector here, this force, 9 kilonewtons. And again, in office hours, I had a lot of questions about the convention for this. The convention for summation of moments is actually, at this point, you guys should be really familiar with it. And if it's not, that's okay. I will explain it now. So if we have the total summation of moments taken about this point, this is point A, and this 9 kilonewton is applying here, you can see that this is causing an overall clockwise rotation. Because if the beam is unhinged here, if we assume that the beam was unhinged, and we see that there's a hinge type structure here, and we're pressing on the beam with this 9 kilonewtons force, obviously the beam wants to rotate like this. This is something similar to, let's say, there's a seesaw. There's a seesaw, and there's a pin here, and the seesaw is connected to the ground. And if I get on top of the seesaw and I press down with my hand, obviously the seesaw is now going to a position shown by this dotted line. The seesaw will go like this if I apply a force. Now, similarly, if I apply a force here, then the seesaw will be in this dotted line. That's the sort of approach we can apply to the beams, because we clearly see that our convention sort of depends on whether the beam is bending clockwise or counterclockwise. Now, returning to their solution of our problem, we say that this 9 kilonewton force is causing an overall clockwise rotation. So that means it has a negative sign, because the convention states if the moment contribution is causing a counterclockwise rotation, then we have a positive moment contribution. So now that we established that we have a negative moment contribution for the 9 kilonewton force, we simply state that we are going 9 times 4 meters, plus we have the B facing up, so it is causing an overall counterclockwise rotation, which means it is a positive sign, and simply we say the magnitude of B times 4 plus 2 is equal to 0. So let's solve these. We rewrite the moment equation as 9 times 4, which is equal to 36, equals B times 6. This is simply B equals 6 kilonewtons. So now that we have the magnitude of B, we can use the total summation of force in the y direction equation, given here, to calculate the magnitude of A, which is A equals 9 minus B, and A equals 9 minus 6 equals 3 kilonewtons. Now that we have the magnitude of A and B, we can solve the moment equations for this beam. So previously, we have shown moments in numerical values. So if I say find the moment about point A, then all you need to do is find literally numerical values for the moment contributions for the 9 kilonewton force and also the reaction force at B. Now we are going to find equations that describe how the moments change as we go across this beam as a function of x, where x is simply the location on the beam. So this is the x-axis. If I say x equals 4 meters, then we're looking at this location. If I say x equals, let's say, 2 meters, then it will be the midpoint of the 4-meter line, of the 4-meter distance. So again, when I draw this and I say the point like x equals 2, and I draw the dot there, I'm actually referring to obviously the location on the beam. That was just drawn here because it is not sort of cluttering the diagram. But anyway, let's section the beam and let's look at what's going on inside of it. So the first thing we need to determine is what interval we are looking at. So if I go A to B and we have certain x values, so this is our x-axis, right? We have certain x values. What do we want our x value to be for the first sectioning of this beam? And let's see. So we have 0 here. We have 4 here. Between these, there are no forces. So the first section is going to be 0 to x to 4. And we will sketch this out with a new diagram. The beam is being sectioned here. It's being cut. It's not being cut in real life, but for the purposes of this inspection. So what are the forces applying? Well, we only have force A because this is our x-axis. Let's draw it up like that. And this is A. We know that we are considering x from 0 to 4, which means that before we can get to this force here, again, x does not get to 4. Before we can get to this force, the sectioning is over. Then we will consider another interval. But right now, we are looking at x is 0 to 4. The only force that applies during the duration of this x is force A, or force A, vector A here. Now, let's draw our beam convention at the right end of our sectioning, because that's where we section, so that's where we want to write our beam convention. The beam convention starts with a shear force here, denoted by, let's say, V1, and we have a moment like this. Let's call this M1, and we have a normal force, N1. So clearly, in this system, there are no horizontal forces, so N1 in this case is not relevant. And especially in the exams, you want to show, I'm not sure if you guys are going to be doing multiple choice exams, but if you're taking an actual written exam, then you want to say no horizontal forces. Write that out, box it. I'm saying this because you want to show that you understand why N1 is not relevant and it doesn't exist, because there are no horizontal forces applying on the system. Now let's solve our beam diagram here for x is 0 to 4, and our summation of forces in the vertical direction is going to be A plus V1 is equal to 0, which shows that V1 is equal to negative A, which is negative 3 kilonewtons. Now let's solve the summation of moments, and let's do this about point O. So I'm going to define with a yellow color point O here. So here will be our point O. So the summation of moments, the summation of moments, about point O, is equal to this distance, which is our moment arm, times the magnitude of A. Notice that this distance is not fixed because we are considering x 0 to 4. So again, I could section the beam here, I could section the beam here, I could section the beam here. Basically, I could section the beam anywhere along this length. Now, going back to our diagram, we see that this distance is defined by x. So, if I want to calculate the moment contribution of A, then we are simply going to look at its clockwise contribution. So we say negative A times x, that is the contribution for the moment of vector A. And again, just to drill this point in, we're simply looking at the force itself times the distance to the axis of rotation. So basically the moment arm. So then we ask ourselves, does V1 have a contribution? Well, the answer is no, because V1 occurs at the point that we section. So it is basically going through, V1 is going through our axis of rotation. And we know that since the moment equation is distance times force, if distance is equal to 0 and V1 exists, 0 times V1 is equal to 0. So V1 has no contribution because we picked our moment axis, so our axis of rotation, which is point O. We picked point O smartly, so we don't even have to worry about V1 here. You often want your axis of rotation at the point you're sectioning, because then it just makes V1 irrelevant. Anyway, now let's look at what other moment contributions are happening. Well, we see moment 1 applying here, and we see that it is a overall counterclockwise moment, so it has a positive sign. So we say this plus m1 is equal to 0. Now let's solve this equation, and we have m1 equals a times x, which is equivalent to 3x, or the units of 3 is in kilonewtons, but we don't need to write that yet. We just need to sort of keep in mind that this is kilonewtons. All right, so far we have information for x is 0 to 4. So we have this distance so far. Now let's look at what happens for this distance here. 4 is smaller than x, which is smaller than 6. This is the distance we're considering, simply this distance. Now, let's draw the free body diagram for that. We have the beam here that we are actually going to section this side. And something important I forgot to add in the previous question was the x and y axes. So this is our y-axis, this is our x-axis. Make sure you add the x and y axes in the exam, or you will get points taken off. Then we have the shear force pointing up, so that's our FV2, and we have the moment contribution. This time, we'll notice that the moment contribution convention is now clockwise and not counterclockwise. So that is our M2. Let me draw that out. It's our M2. And we previously stated that the horizontal forces are equal to 0. So the normal force, the horizontal normal force for this diagram is irrelevant. Now let's define our distance. So we have, one important thing I forgot to add. There's a vector here. There's a force, this is our force here. It's force B. Now let's define this distance. So let's look at the overall diagram really quick. If this is our whole beam, and this distance is 6 meters, right? So if we're looking at, let me just highlight the fact that this distance is 4, and our x is now relevant to this distance, right? So this is our x. So if I want to look at, let's say, this section, right? Let me use a different color for that. If I want to look at this section, how can I describe algebraically what point in the beam I'm looking at? Well, we know that this distance is x, right? And we also know that the total distance is 6. So if I want to look at this distance, then we're looking at 6 minus x. Because if I do 6 minus x, then I get this, right? And since we sectioned from this end to that end, what I'm saying is the sectioning is here, as opposed to the usual sectioning on the right side. When we section off the left side, we try to derive the distance we are looking at in terms of the values that are already given to us. And we see for this case, 6 minus x is a great way to represent that, because I don't know if there's another way, but this is definitely a correct way to represent it. Also, one thing to note is that the x we are considering is 4 to 6. So why is this important? Well, because notice when I said 4 here, right? So if we do 6 minus 4, where possibly the lowest value that x can get is 6 minus 4, then we're looking at 2. So then this equals 2, right? So for the smallest x, we are looking at exactly this direction, because if this is 2, then this is 2, and we're looking at this location, right? Now, if x is 5, let's say, so let's make that 5, x is 5, then it's equal to 1. So then this distance is equal to 1. Then we would be looking at this location, where the distance between B and our sectioning is equal to 1. Let's do that again with x equals 6. We know that 6 minus 6 is 0, and if this distance is 0, then we are looking at the location at which the beam ends. Now, let's return to our problem. We have this distance defined as 6 minus x. Let's create some space. And then we solve this problem using summation of forces and summation of moments. And to start off, I'm going to define this as point 0. Sorry, point O. Let's do summation of forces in the y direction. We get V2, which is our shear force, plus B is equal to 0. So then solving this, we get the shear force is equal to negative B, which we define B to be 6 kilonewtons. We have negative 6 kilonewtons for the value of V2. Then we do the summation of moments about point 0, about point O, and we have the contribution of this moment, which is going to be negative because we are going clockwise. So that's negative m2. And then we have the contribution of vector B, which is an overall counterclockwise rotation, because our axis of rotation is point O, and B is causing an overall counterclockwise rotation. So now let's get this in terms of actual algebraic values, and we get B times 6 minus x equals 0. Solving this equation, we can find an algebraic expression for m2. Let's do that. So we get m2 is 6 times 6 minus x is equal to 36 minus 6x. So now we have complete expressions for the entirety of x. So we have complete expressions for x going from 0 to 6. This means that we can now plot. The expressions we have, which means that we can create our shear and moment diagrams. So let's do that. I'm going to draw two graphs. So let's start with a shear. So this is our overall format. So we have shear force here, and its units is kilonewtons, and then we have moment here, and the units are kilonewtons times meters. It's a little cluttered, so I'm going to move this a little down. Much better. We have the two functions for x is 0 to 4. So for this distance, we have shear equals to -3 kilonewtons. So let's mark that on the graph. We have -3 kilonewtons here. And it is going to be, let's say this is x equals 4. It is going to be continuous like this and up until x is 4. And then we have shear force V2, and it's going to be equal to -6 for this duration here. So then let's do that. That's going to be -6 here, and that jumps from -3 to 6 and continues until we have x equals 6 here. So that is our shear force diagram. Now let's do the same for our moment. We see that M1, which considers 0 to x to 4, so it's going to be this interval, defines the moment as 3x for that interval. And I realize that I need to make a change to my diagram here. So let's do that. Much better. This gives us that space to plot our functions. So M1 says 3x. Let's look at what 3 times x equals 4 is, and it's 12. So we're going to have 0 to 12 linearly. So that's going to be 12, and that's going to be 4. And let's show this as 12. And then we have 36 minus 6x. So let's show this. Let's see what it is at point x equals 4. So then we have 36 minus 6 times 4. We know that this is equal to 26, so that equals to 12. So this section of our graph will have an initial point here because we simply inspected. You can think of M2 as something that looks like this. M2 as a function of x gives the value of M2 when an input of x is received. So if I say M2 4, then 36 minus 6 times 4 is equal to 12, right? So this can give us this definition, this algebraic definition of M2 can give us the value at each x location that we are considering. So then let's do that. We have 12, and this 12 starts and decays to, let's see, we have M2 at 6. What does it decay to? We have 36 minus 6 times 6, which is equal to 0. Oh, we see that this linearly decays like this. Let me draw that better. Like that until x is equal to 6. Let's clean up the graph here a bit. So that's 6, that's 4, and this is our overall moment diagram. Email me if you have any questions, and have a nice day.